Thank you very much indeed for that. So, once again, I mean, I've been working in earth and clay structures for about 30 years, and I come along today and I found out something that I didn't know before, which is fantastic. And it's, you know, just a little clue to us that materials that we think we know and we think we know how to work with, actually there's still a lot more to learn, a lot more to discover, a lot more to research, and then to diffuse that information so that other people can try these things out. Because just with a little bit of information, you can take your material and you could apply it on Lizzie's site and bring a very small amount of something else and get a big improvement. So you've got this sort of connection between, very real connection between people's actual situations and the knowledge that that we're gaining. So that's fantastic. Are there any questions? Oh.
Going back to the first speaker, I was quite intrigued by the home build, if you like, using natural local resources. Of course, this has been the way we've been building for thousands of years. Virtually all the cathedrals in Britain have been built out of relatively local stone. This is something I didn't realize until quite recently. Further than 25 miles away, it simply wasn't economic to obtain this stone and build a cathedral. So that's very interesting. One little thing that I spotted, which I'm quite interested in, is the depth of the foundations. I assume you're on some fairly firm rock where you were building there, and I noticed a 500 millimeter base. How does that get on with building regs? What have you found in relation to local authorities giving you permission to build basically pretty close to the top of the soil? Thank you.
Is this on? Yeah, this is on.
Yeah.
So this isn't a drawing that's been through building regs. This is it's an initial proposal, and it would need definitely more detail. It's not to scale. The ground is quite firm. The rock is quite near the surface, so the top. It's a sloping site with the top, quite thin topsoil really. So it doesn't take long to get down to the stone. And the width, you said? What was your?
I just wondered how the 500 millimeter base, was that sufficient to get permission? You've told me that you haven't submitted this for building regs, so you don't know whether this design will be approved through the planning system.
No, this hasn't been submitted, and it's not something. It's a theoretical exercise. It's not going to be built according to this drawing. It's a very quick conclusion from the site materials as a starting point really, and it would be developed quite a lot to get to that stage. So it's more kind of gathering of information and initial proposals.
Hold on. Can you say that again?
I would need to know if I was one of the volunteers wielding the shovel.
But back to your comments on local construction, it's a reminder really that this is a traditional way of building. This gathering your materials, which if you're in an urban situation, there's also a lot of local material that is available. There's a lot of talk on the waste site yesterday about materials banks and being very intelligent about where these banks of materials are and how we use them and logging them, providing materials with passports that, so we know where they are and how much of them there are, so that we can then go and get them and reuse them. So it's not just about virgin materials off a site like this. It's about being clever with other resources we have in different environments. And as I said, my research in Gaza went into what materials are available that without bringing them over the blockade, basically.
And it's about being clever with what we know and what we can calculate. Just round the corner, you'll see H.G. Matthews' stand. They're building a big clay dome on a trench foundation filled with gravel and blinded with limecrete, 150 millimeters at the top. and that's basically been signed off by an engineer. So it doesn't sit within building regs. It sits within the skill of the engineer. And these are things that we, I think, consistently rely on to do to work for us, because building regs are very tightly defined by products, and now we've stepped out of products and into materials that we can find and that we can manipulate, and that we have been manipulating for thousands of years, and we have greater skill now potentially to calculate and use at site.
Yes, I wanted to ask about the clay renders. Firstly, what thickness do they need to be applied? And secondly, do you have a sort of an idea of a lifespan, maybe based on somewhere in the world?
I haven't heard your second question. I haven't heard your second question. What was it?
The first part was what thickness do you
yes,
need
all right.
to apply?
Yeah.
Second is sort of design life. So
right.
what its sort of lifespan would be.
Lifespan, right. Both questions really crucial. The renders during my master were designed having 25 millimeters, as common renders have. But during my my dissertation, during my master and my PhD work, I found that we can minimize the depth, because the material is so waterproofing that finally it doesn't require to have such a depth, such a width. So we can reduce the millimeters finally. As for the lifespan, it's really crucial, and we're working on this, because according to the constituents used, the lifetime is relevant, because if you use organic material that have a shorter lifespan and are susceptible to external weather conditions, oxidation or decomposition or whatever, this decides the lifespan. If you use synthetic that can dispose at the end, the lifespan is different. So it's according to the constituent you use as for the waterproofing agent. Yeah. But I think that there is a potential that the lifespan is considerable. I mean, this is important because every 5 years, as we said, in the Latin America or Africa or whatever, there are earthen cities that they required reapplication of clay-based renders, sort of in a very after 5 years, but 5 years is too long. They have all the material has degraded, so we can develop this to have a larger lifespan. This is important, really important. Yeah.
Considering the second question from the guest here, how do you minimize the thickness in the building that already exists? Because I'm from Egyptian background.
Right.
Okay, and we are trying to do this for our historic buildings, especially the old ones. And the second question is there materials, technique materials that you can add inside to be injected inside the material stuff, like for the mortar or clay, whatever, so we can get out this water embedded inside the block itself, or whether the stone or the brick or whatever?
You mean to inject the render?
Yeah, because I took a training. It was in one of the conservatives building, and I found the worker used to inject material inside and wait for do tests, and then later they check by maintenance every year that if this block is still getting out the water or not.
I see.
Yeah, I mean the water vapor. Sorry.
Right.
So this was your master. Considering your master's degree, the
part of, yes. I'm an architect. That's why I'm interested in this.
Yeah, me too. I'm an architect.
All right.
Okay.
I got it.
And the second question was how, if you have a building already exists.
Yeah.
So how you minimize the thickness, which is already present.
I
and
see.
how and this will affect the building itself, like it can collapse, for example, or something?
All right, I see. Right.
Okay.
Regarding the second question, regarding the thickness, it depends, really. It depends, because we have to know first the substrate. First, the condition of the substrate. If they have humidity, high humidity levels, or if it has undergone a flood, or it is under stress. All these parameters are important in order to see the depth, the width of the material. But the larger it can be, it could be 25 millimeters. It's too much, I think. It could be reduced, significantly reduced. It could be reduced to 10, I personally think. But we'll find it during our research. I think 10 millimeters are not too much. I think so. Of course, it has to be firstly to acknowledge the building requirements, state, heat static conditions. There are too many parameters to consider, but it can be reduced to 10 millimeters. I'm sure. I think so. It should be. Yes, I think so. Yeah. All right.
So there's also quite a lot of work on, so two things, thoughts that came to my mind. Number one is that simple solutions tend to be more effective than complex solutions. So Lizzie showed French drains in her design, taking away the moisture in and around the building to stop that flow of moisture coming up. And then the other thing that I know is an issue in Egypt and a lot of other places is this salting question, which you referred to in your talk. And there's quite a lot of work on sacrificial clay coatings, where the clay is used to take salt, draw salt out of the structure. So you're plastering, the salt's drawing into the clay, you're removing it, you're plastering again. And that might be an application that you have to do, a number of cycles to get it right. If you've then dealt with your site conditions, with French drains, simple methods like that, so that you're reducing the amount of moisture around, it will then hopefully prevent that drawing up of further salts. Once you've done that, get yourself some waterproof render.
Morning. I'm interested in Andronika's work on the clay renderings, and you experimented with different sorts of additives to the clay. I know nothing about clay, but I'm assuming that there might be different sorts of clay. And I'm wondering how you considered that and how you made a choice of one, I presume just one, for your comparison work.
You have to start from this was a master dissertation which was completed within almost 7 months. So the limitation of time was crucial for the decision of the material. So I choose one because I have made a scrutinized research in academic literature to pick the material that had more potential to perform. So I picked sandy clay because I have researched it and I have indications that this specific clay could be more, let's say, efficient to my research. But during my PhD, I'm researching different kinds of clays in order to compare them and finally select the right choice. So also slag could be added, because then the embodied energy of the material at the end could be even lower. So clay could be a small percentage, and slag, which are very efficient also, could be a larger percentage in order to develop and enhance the properties of the material.
Yeah, I mean, clay has got this enormous spectrum from kaolins, which are quite inactive, or through to bentonites, which are very active. I think this is really a call. I think you're really giving a call for a bit more funding to go into organisations that are researching these materials, because you start with an idealised clay and give yourself a picture of what's happening there, and from there, we need to build into, work into those other clays and those other materials. We've got, in this country, we've got everything from kaolin to bentonite, but in some of these places, you've got clays which are weathered tropically, like laterites, and they have a whole, they've got different properties, and they also need looking at and researching. CAT are a charity. Earth Building UK and Ireland are charities, and the way that we get funding is not through commerce, but through donation. I'm just saying. Please be a member. Do we have any more questions?
Thanks. It was very interesting. You did mention that there's still more testing to be done. So my question is, you looked at vapor permeability and water absorption. Which characteristics did you try to maintain to keep it comparative to the traditional materials? Which type of characteristics or properties did you cut off or did you maintain so that it could still be considered comparative?
Very crucial question. We try to combine all properties possible. So these are the two properties that I presented here. But the selection of the specific constituents are made from the start in order afterwards to have as efficient, as high performant, as let's say efficient material complying to most of the properties required. Because all the properties could be, very important property could be the freeze-thaw cycle property, to adhere, to resist to the freeze-thaw cycles. This is important in cold countries. This is very important. So, because the material degrades during the cycles. Another property required that we look for and we select the materials accordingly is abrasion resistance. Because if the external coating can be resistant to abrasion, then it can be durable. And this is what we look for, durability and high performance also. For example, if abrasion resistance diminishes during time, then waterproofing would be affected. That's why. Also, other property could be adhesive strength, because if the material is binded well with the wall, then the endurance of the material would be higher. So we acknowledge all these properties. We try to combine all these properties, but if some of them cannot be combined, we'll compromise. But the selection of the material is very wise based.